Rocket engines hate being mass-produced. They are built to handle controlled explosions, which means they are usually built like Swiss watches. You machine them slowly, you check every seal by hand, you treat each one like a rare jewel because the forces inside are trying to melt it. That approach works fine if you only need a few engines a year. It fails completely if you need to build a fleet, and that is the wall SpaceX had to break. The physics of a rocket engine sets a hard limit on how fast you can build. You have fire burning at thousands of degrees. You have pumps spinning at crazy speeds. You have pressures that can rip steel apart. If you rush the build, the engine explodes. If you take your time, you never have enough engines to fly often. That trapped the industry for decades. The only way to get reliability was to go slow. But SpaceX needed a river of engines. A single super heavy booster needs 33 engines. A single ship needs 6 more. To build a fleet of starships, you need thousands of engines. You cannot build thousands of engines using the old method. It would take a century, so they had to turn the engine into a factory product. They had to make it something you can build in days, not months. This is the story of how they did it. It is not about a magic design, it is about a factory machine in McGregor, Texas, that turned the impossible into a daily routine. The place does not look like a high-tech lab. It sits on about 4,300 acres of flat Texas land. It is full of concrete stands, steel pipes, and loud noises. But inside the buildings, a different kind of machine is running. It is a production line built to push out Raptor engines at a rate of 2 to 4 every single day. Think about that number for a second. 2 to 4 rocket engines a day. In the old world, getting 4 engines done in a year was a victory. The RS-25 engine, which powers the SLS rocket, has a production rate capped around 4 units per year. That is not a knock on the engine. It is a result of how it is built. It relies on complex machining and hand-brazed tubes. It relies on a supply chain spread across the country. It was designed in an era where you flew rarely, so you could afford to build slowly. SpaceX could not use that playbook. They needed speed. So they changed the rules of how metal gets shaped. The breakthrough came from a specific technology called laser powder bed fusion. That is a fancy name for high-end metal 3D printing. They use machines like the Velo 3D Sapphire. These are not toy printers. They use lasers to melt metal powder into solid shapes, layer by layer. This changed everything because it removed the hardest part of building an engine. In a traditional engine, complex channels for fuel and cooling have to be made from many small pieces. You have to weld them together. Every weld is a weak spot. Every weld takes time. Every weld is a chance for a leak. With these printers, SpaceX can grow those complex shapes as one single piece. They can print the cooling channels directly into the wall of the combustion chamber. They can print the housing of the turbo pump. A turbo pump is the heart of the engine. It shoves fuel and oxygen into the main chamber at huge pressure. It has to handle extreme stress. Making one the old way took months of cutting and fitting. Printing it takes days. They cut the part count by huge margins. In some cases, they replace 10 or 20 bolted parts with one printed block. That means no bolts to vibrate loose. It means no seals to fail between those parts. It means less time on the assembly floor. This is resource efficiency in its purest form. You save time, which saves money. You save weight, which lets you lift more payload. And you save the inspection time needed to check all those old joints. But printing is only the first step. The real magic happens when the parts hit the assembly line. McGregor is not just a test site anymore. It is a factory. They set up dedicated lines where engines move from station to station. It looks more like a car plant than a rocket shop. Robots handle the welding for the large joints. A robot does not have a bad day. It does not get tired at the end of a shift. It lays the same bead of weld every time. That consistency is what allows you to speed up. But building fast is dangerous if you don't test fast. And this is where the system mastery at McGregor really shows up. If you build 2 engines a day, you have to test 2 engines a day. You cannot let them pile up. So they built a testing machine that matches the production machine. They have 5 test bays running like a drum beat. They have a new vertical stand that can handle intense firing schedules. The goal is to run over 1,000 tests a week. That number sounds impossible. It includes testing valves, testing pumps, and firing full engines. It is a flood of data. Most programs test to prove an engine works. SpaceX tests to find out when it breaks. There is a huge difference. When you have a river of engines, you can afford to push some of them to the limit. They run torture tests on purpose. They fire an engine for 201 seconds. That is over 3 minutes of full power. It is long enough to heat soak every part of the metal. It is long enough to find weak spots that only show up after minutes of burning. If the engine survives, it is proven. If it fails, they tear it down. They have a team dedicated to failure teardowns. They pull the broken engine apart. They look at the melted metal. They look at the cracked seal. They find the root cause, then they fix it in the design and print a new version. Because the printers are fast, the fix can be on the test stand in days. In the old world, a failure meant months of meetings and reviews. In this world, a failure is just a data point that tells you what to fix next. This loop is the secret weapon. Build fast, test hard, break it, fix it, repeat. That is how you take a machine as complex as a full-flow staged combustion engine and make it reliable. The Raptor uses a cycle that is notoriously hard to master. It uses 2 pre-burners. One burns fuel-rich, the other burns oxygen-rich. They drive the turbines that spin the pumps. Then all that gas goes into the main chamber to burn again. It is efficient, but it puts heat and stress everywhere. Many experts thought it was too complex to mass produce. They said you could build one for a lab, but not hundreds for a fleet. SpaceX proved them wrong by simplifying the plumbing. On the newer Raptor 3 designs, they moved a lot of the plumbing and sensors to the outside or integrated them into the printed structure. They removed heat shields that were needed on earlier versions. They made the engine cleaner. A cleaner engine is faster to build. It is easier to fix. If a sensor goes bad on the stand, you can swap it without taking the whole engine apart. That matters when you are 30 seconds from a test fire. You don't want to scrub the day because of a buried wire. You want to fix it and fire. This focus on repairability is a sign of a mature factory. They are not just chasing performance numbers. They are chasing operations. They know that a rocket on the launch pad is useless if it takes 6 months to service. They need engines that can fly, land, and fly again. The testing routine at McGregor is brutal. Before an engine is cleared to ship, it goes through an acceptance gauntlet. It starts with spin prime tests. They spin the turbopumps up to speed using gas pressure without lighting the fire. They do this 10 to 13 times. They want to prove the pumps can start and stop repeatedly without binding up. This is critical for Starship because the ship has to restart its engines in space to come home. It has to restart them again to land. A single failure to start means the loss of the vehicle, so they hammer the start sequence on the ground. Then they run the pre-burners. They look for clean ignition. They look for stable pressure. If they see a weird flash or a pressure spike, the engine fails. It goes back to the line. Only after passing these gates does the engine get to fire at full power, and even then the computer is watching everything. If a single sensor drifts out of the safe zone, the test cuts off automatically. This is justice through consequences. The physics decides if the engine is good. You cannot talk your way past a pressure sensor. You cannot negotiate with a temperature reading. The engine either works or it doesn't. This rigorous testing creates a pool of trusted hardware. Once an engine passes, it gets shipped to Starbase or Florida. It becomes part of the inventory. This is a strategic shift. In the past, engines were the bottleneck. You waited for them. Now engines are becoming a commodity. You have a stockpile. If a booster needs 33 engines, you pull 33 from the shelf. If one looks bad during a check, you swap it for another one. You don't delay the launch for months, you just grab a spare. That is how airlines work. That is how trucking companies work. And now that is how rockets work. The contrast with the rest of the industry is stark. While McGregor is pushing out engines daily, the legacy supply chain struggles to deliver a handful a year. The RS-25 is a marvel of engineering, but it is trapped in a slow system. It costs over $100 million per engine. The Raptor aims for a cost of around $250,000. Even if they miss that target and land at $1 million, the gap is massive. You could build 100 Raptors for the price of one RS-25. That cost difference changes how you think about risk. If you lose an RS-25, it is a national disaster. If you lose a Raptor during a test, it is a Tuesday. This low cost allows SpaceX to take risks that others cannot. They can try a new alloy. They can try a new weld path. If it fails, they are out a little bit of money and a few days of time. They are not out a year of budget. This freedom to fail is what drives the learning curve. You learn more from breaking 5 engines than you do from polishing one. And because they are building so many, they have plenty of engines to break. The target for the future is even wilder. They are aiming for a production capacity of 800 to 1,000 engines a year in the near term. Longer term, for a full Mars fleet, the math points to 4,000 engines a year. That is automotive scale. It requires a supply chain that moves mountains of metal powder. It requires a training pipeline that turns regular mechanics into rocket technicians. It requires a quality control system that never sleeps. You can see the signs of this scale-up at the site. They are building more assembly halls. They are adding more test stands. The infrastructure is growing to match the ambition. This is not just about building a rocket. It is about building a logistics train that can support a civilization. If you want to send 100 ships to Mars, you need thousands of engines, you need spares, you need cargo ships, you need tankers. The engine factory is the foundation of all of it. Without the engines, the ships are just steel towers. The use of materials like Inconel and GRCOP42 is another key detail. Inconel is a superalloy that keeps its strength even when it is glowing red hot. GRCOP42 is a copper alloy that conducts heat incredibly fast. It is used in the combustion chamber to pull heat away from the walls so they don't melt. Printing these materials is hard. Copper reflects laser light, which makes it tricky to melt. SpaceX had to master the printer settings to get it right. They didn't buy this knowledge, they earned it through trial and error. That knowledge is a moat. Even if a competitor buys the same printer, they don't have the recipe. They don't know the exact laser power or scan speed that works. SpaceX does. There is also a human element to this factory. The people working there are running 24/7 shifts. It is a grind, but it is a grind with a clear score. Every engine that ships is a point on the board. Every successful test is a win. The culture is built around results. In many aerospace companies, you get rewarded for following the process, even if the result is late. At SpaceX, you get rewarded for shipping reliable hardware. That attracts a certain kind of person. It attracts the person who wants to see their work fly, not sit in a meeting. The near-miss moments in testing prove the value of this approach. There have been times when a seal failed seconds into a test. The safety system caught it and shut down the engine. In a program with only a few engines, that would be a crisis. At McGregor, they just pulled the engine, fixed the seal design, and ran another engine that afternoon. The momentum never stopped. That resilience is what makes the program scary to competitors. You cannot beat a team that can recover from failure in hours. The Raptor 3 engine is the latest evolution of this philosophy. It pushes the thrust up to 280 tons. It pushes the efficiency up. But the most important number is the part count. It has fewer parts than Raptor 2, it has fewer flanges, it has fewer bolted joints. It is designed to be built by machines. This design for manufacturing is the final piece of the puzzle. You don't just design an engine that works, you design an engine that can be made. If you look at the trajectory, the gap is widening. Legacy space programs are still operating on timelines of years. SpaceX is operating on timelines of days. They have turned the impossible physics of rocket engines into a standard production problem. And production problems get solved by volume. The more you build, the better you get. The better you get, the cheaper it becomes. The cheaper it becomes, the more you can fly. This cycle has created a machine that feeds itself. The factory feeds the test site feeds the launch pad feeds the data back to the factory. It is a closed loop of speed, and right now, that loop is spinning faster than anything else in the industry. The result is a level of dominance that is hard to overstate. When one player has the ability to produce the most difficult part of a rocket at a rate of thousands per year, they control the pace of the future. The engine was supposed to be the bottleneck. It was supposed to be the reason Starship would fail. Instead, SpaceX turned the engine into their biggest advantage. They did it by ignoring the old rules of how to build. They embraced printing. They embraced testing to destruction. They embraced the grind of daily production. And in doing so, they turned the Raptor from a science project into a commodity. That transformation is the real breakthrough. It is not just about going to space, it is about building the industrial base to stay there. The factory in Texas is the proof that it can be done. It is loud, it is dirty, it is full of fire and noise. But it is the most important building in the space industry today, because without it, there is no fleet. And without a fleet, there is no Mars. The engines are leaving the factory gate every single day, and that rhythm is the sound of the space age finally shifting gears. The competition is stuck playing a different game. They are trying to perfect a handful of engines while SpaceX is building a stockpile. It is like a craftsman trying to race an assembly line. The craftsman might make a beautiful part, but the assembly line will change the world. The numbers on the scoreboard are clear: 2 to 4 engines a day, thousands of tests a week, a cost that keeps dropping. This is not a promise of what might happen. This is a report of what is happening right now. The machine is running, and it is not slowing down. This leads to the final realization. The barrier to space was never just gravity. It was cost, and cost is driven by volume. By solving the volume problem for the hardest part of the rocket, SpaceX has cracked the code. The Raptor factory is a weapon of mass production. It creates a capability that no government and no other company can match today. It is the engine of the future, built in the middle of Texas, one laser-printed layer at a time. The impossibility of mass-producing rocket engines has been solved. The rest is just logistics.